Complex numbers, we remember that we write them as in general a plus bi, so a is a real number, b is a real number. So here we have real part and then we have imaginary part with I is radical -1. So we said that we can represent these numbers as points in a plane. So we remember also the polar coordinates. We remember it was very similar to what we have here. X was r cos of the angle and y was r sine. So miracle, miracle. Our complex number is a point in the plane, and A is on real axis or X, and then B is on imaginary axis or Y. So we have the same formulas. A is r cos of the angle, so angle that we make with the x-axis. Here it's also called the argument, but okay, it's just an angle of the ray with the x-axis. And B would be r sine, so this is exactly like our polar coordinates. That's why it's called polar form of the complex number. So essentially now A, we replace it by r cos, and B by r sine. So now r is common in both, so we can factor it. So we can write it this way actually. Why is this useful? We will see very quickly. So Z is our standard, is equal to our standard writing of the complex number, and then this writing here is polar form. R is obviously the distance, which is modulus or the absolute value of the complex number, and theta, as we said, is the angle between x-axis and the ray that connects origin with the point. So this is the standard writing of complex number, and this is a polar form. So they are equal. R is the modulus and theta is the angle here. So essentially, for any complex number, we can write this. So they are the same, and then we can maybe put some power much easier and compute some of the operations that we already saw. Elementary operations may be easier than usual. So we said R is this distance, so it's the modulus of the complex number, and then B over A is tan of the angle, so that's what we have. This is the equation from which we are going to find the angle theta by tan inverse, and also we will pay attention to the quadrant in which we are to pick the correct value of theta. As a reminder, we know that Z times conjugate of Z is a squared plus b squared, which we see here is modulus squared, which is r squared, right? So that's the same. We know that if we spin another circle around, another spin, we will have the same point. So that's why the argument or the angle is always can be written with the angle or plus 2 pi or minus 2 pi, whatever is more useful to us. But normally we try to keep it simple and keep only one value of theta. So now what happens if I want to multiply two complex numbers? Well, obviously we can proceed as we normally do, this binom times this one, and then we proceed step by step. But we can also use this polar form to perform the product. So we can do it step by step, and we will realize actually that it is r, so the modulus of the first and the modulus of the second, then cosine of sum of the angles plus I sine of the sum of the angles. So if we do it for one, we will realize quickly, because of the cross products and stuff, that this is the case. There will be some other ways to write this in a maybe more compact way also, and it will appear easier, but this is easy just by the procedure we can find this result. Now if I perform the division, as we said, we normally use the conjugate multiplied by upstairs and downstairs of the conjugate of the denominator, blah blah blah. But you see here in this polar form, the result, well, if we can do it, but the result is simply ratio of the modulus and then cosine angle of the first minus angle of the second, and I sine angle of the first minus angle of the second. So that's interesting. This is much faster than doing the procedure as we would normally do using the conjugate. Again, 1 over z, we can do it step by step, but again it's just this with the minus here and 1 over r. So suddenly this polar form will simplify some of the computations, especially when we start computing the powers of complex numbers. So we have a result for the powers of complex numbers called the Moivre theorem. So essentially we can put our complex number to any positive integer power, so power 2, power 3, power 75, and then since this is our z in polar form, to power n, well, so n is distributed, and you see what happens with the angle is multiplied by n. So essentially putting to power becomes extremely easy. Obviously these results can be proven step by step. If we come here, if z1 is equal to z2, we can see it immediately. It's going to be 2 times theta, and r times r squared. So something that respects the formula, obviously, and then we can go step by step. But for now, we just remember this result. So suddenly, by writing our complex number in polar form, putting that complex number to a power is much simplified. So another way to write the complex number will be also using the Euler's formula. So just to see how we get there. So if I put a complex number as a power of exponential, what happens? So we can do this and go step by step, and then we will realize that exponential of a complex number will result in something like this. Knowing the series for the sine and cosine, we'll get something like this. No need to do the details, but that's the Euler's formula that's coming from this development here. So essentially, e to power a complex number is e to power a, so the real part, and then cosine of b plus I sine b. So essentially, we can write our complex number in polar form, and then it can be written using the Euler's formula here. So the angle is the same as what we have here. So if we have theta instead of b, we could have cosine theta plus I sine theta, so that's what we have here. R is multiplying R here, right? Copy paste. So essentially we have 3 ways of writing a complex number. Standard way, a plus ib. We have this polar form, and then we have Euler form. 3 ways of writing the same complex number. One of them is more practical than the other for certain operations. So now when we have this exponential form or Euler form of the complex number, putting a complex number to a power, well, z to power n, r to power n, and then exponential to power n, so the n is here. So suddenly we realize why the formula that we got, r to power n and cosine with n theta, is what it is. So from here it's easier to see from this Euler notation of the complex number, and then when we put to the power n, we see the n's, and here the angle is modified from theta to n theta. So that's what we have here. So suddenly putting complex numbers to powers is very easy. Again, r is the distance, so the modulus a squared plus b squared radical, and then the angle, we get it from the relation tan theta equal b over a. So again, we need to pick the angle that will correspond to the correct quadrant. So we will see some examples with that. So this is just a summary of the result, our standard notation for complex number, polar form, and then Euler formula, Euler form. And then these are the pieces. What is r is the modulus, and then the theta comes for here, the angle that we need. So that means that we can write one complex number in any one of these three ways. So let's say I'm given e to power I times 0, so write that as a number, the complex number in a standard form. So here angle is 0, so we have cosine 0 plus I sine 0. So simple application of the Euler formula. Cosine 0 is 1, sine 0 is 0, so we get 1. Wow. Exponential I times pi, so again angle is pi here, application of Euler formula, cosine pi plus I sine pi, and we compute I pi over 2. So essentially we see one notation which is Euler form, and then we have just expand it, and then we get the standard form of the complex number, which means also we can go the other way around. From here we can find the angle and the r. So let's say we have a complex number given in a standard form and we want it in polar form. Polar form meaning we need r and we need the angle theta. So how do we get r? R is the modulus, so it is real part squared and then imaginary part, the coefficient here squared. So 1 squared plus 1 squared, it's 2, so radical 2. So that's the r, is the modulus. Now what is important is to realize that this complex number is in the first quadrant because we have plus 1 and then plus 1 here also, so it is in the first quadrant. So when we look for the angle now, we know that theta of the angle is b over a, so 1 over 1, which will be 1. So tan of the angle is 1. When we do tan inverse, we need to take the angle that is in the first quadrant, which is pi over 4. So now we have r and we have the angle, so we can write our complex number as r times the Euler form. So cosine of the angle plus I sine of the angle. So that's the procedure. Again, we need to be careful about the angle to be in the correct quadrant. Here, another complex number given in a standard form, so minus 1 minus I. So we realize we are minus 1 in x and minus 1 on y, right? So we are in the third quadrant. So we need to be careful, our angle needs to be in the third quadrant. So again, minus 1 squared plus minus 1 squared, so that's 2. We take the root, so we get our modulus, r, and then tan of the angle is minus 1 divided by minus 1, because here coefficient is minus 1, and here also, so b divided by a. Again, tan theta is 1, so we need to take tan inverse, but we need to be careful. We need to pick the angle that is in the third quadrant. Angle in third quadrant whose tan is equal to 1. So obviously it's not pi over 4, it's 5 pi over 4. So we need to be careful from the point here from the complex number, we know in which quadrant we are on the plane. So we need to pick the angle in the correct quadrant. And then we just rewrite r times cosine of the angle plus I sine of the angle. So here we were in the first quadrant, 1, 1, and here we are -1, -1, so we are in the third quadrant. So we need to be careful about that. So that would be probably the first thing. Draw the plane and then sketch the point in which quadrant it is, so that way you don't make any errors with the angle. Obviously we are not going to make any errors with the modulus, so that's not an issue, but the angle is the problem. So what happens if I have a complex number and I need a polar form? So here z is I, so that means we have 0 plus 1i, right? So 0 plus 1i. So the modulus is 1, so that's fine. And the angle here, how do we compute the angle? Because we will have 1 divided by 0, that's not good. So if we try to draw this on our plane, we will have 0 on real part and 1 on the imaginary axis, right? So x is 0, y is 1, so angle that we make is pi over 2. So just from the sketch we know the angle immediately. So that's very important. Probably the most useful thing would be to draw the plane and then locate the point on the plane to have a better idea of the angle. So here angle is pi over 2. Modulus is 1 because 1 squared plus 0 squared is 1, and then radical is still 1. The point here is minus I, so it is 0 on real axis, so 0 on x, and -1 on y. So where is that? So if we draw it, it's 0 on x, -1 on y, so we are here somewhere, so that means angle is 3 pi over 2. So from the sketch we could figure out the angle. Z equal 1, what does it mean? Well, we are on real part is 1, so x is 1 and y is 0, so angle is 0. So cosine 0, I sine 0, obviously the modulus here is 1 again. Z equal -1, so where are we? We are on the negative side on the axis, and on the y-axis we are at 0, so essentially again modulus is 1, but angle is pi. So that's why we write it. Okay, you could say it's minus pi also, fine, but we keep the simplest one. So the first thing is probably to draw the plane and then sketch the point. That will simplify the work for the angle. So here a complex number that is a little bit more involved. So on x-axis or on real axis we have radical 3, and on y we are on imaginary part -1. So that would be radical 3 -1. So that's quadrant number 4. So first thing when we sketch, we know we are in the quadrant number 4. So first thing now to write it in the polar form is to find r, the modulus. So first a squared, so that would be 3, plus -1 squared, so 3 plus 1 is 4, radical is 2, so we have our r, the modulus, and then tan of the angle is -1 divided by radical 3, so b divided by a, and we know that our angle needs to be in the fourth quadrant, so either you use the negative angle or you can add 2 pi and then write as 11 over 6 pi, 11 pi over 6. It's up to you, do you keep negative angle or positive, that's not a big deal, but what is important is to be in the fourth quadrant, because our complex number is in the fourth quadrant, right? X is positive, y is negative. So now we have r, we just use the formula, r times cosine of the angle plus I sine of the angle. So those are simple procedures, just need to be disciplined and pay attention to the quadrant in which the number is. So if I need to do the product of two complex numbers, obviously if we do it normally it's not a big deal, but if we do it in polar form, as we said, we first need to find r and the angle for each, and then the product is product of the r's and then sum of the angles, right? Here the angle was minus pi over 6, that's why you have minus. So it was product of the r's and then cosine of the sum of the angles plus I sine sum of the angles. Again, one of the angles was negative here. And then we simplify. So what happens if I have the Euler expression? So I would need to use Euler formula in order to get the standard notation for the complex number. So e to power I pi, so it's cosine of pi plus I sine of pi, and then I evaluate. Cosine pi is -1, sine pi is 0, so that's why we get at the end -1. So step by step, there's no rushing here. Exponential of -1 plus I pi over 2. So we have exponential -1 times exponential I pi over 2. So exponential -1 times exponential I pi over 2. We use the Euler formula for that, so it will be cosine pi over 2 plus I sine pi over 2, step by step. So exponential -1, 1 over e, cosine pi over 2 is 0, sine pi over 2 is 1, so we get our complex number. So here the real part is 0, the complex part is 1 over, the imaginary part is 1 over e. What happens if I have e alone? So e is e to power 1, obviously. So if I want to write it properly, I could write it this way. So with angle 0, so I get something like this. Okay, it doesn't look very sophisticated, but okay, step-by-step procedure. We don't need to think too much, we just do it properly. Here we have e to power pi plus I, so this is e pi times e to power I, right? E pi times e to power I, angle is 1, right? E to power 1i, so we apply the Euler formula, cosine 1 plus I sine 1. So we get some fancy complex number. E to power I pi over 4, angle is pi over 4, using the Euler formula. So we get, obviously we need to evaluate cosine pi over 4 properly and sine pi over 4, so we get a standard form of a complex number. Now the usefulness of this notation, of the power notation, is when we compute the powers of the complex numbers, because that's really where it shines. Why? If I have a complex number to power 10, so obviously I'm not gonna do the product of this number 10 times by itself. There's no point. So what do? If we rewrite it in a polar form, so we need to find r and we need to find the angle. So r is this squared plus this squared radical, and then angle here is 1 over 2 over 1 over 2, which is 1. So tan of the angle is 1, and we are in the first quadrant, so angle is pi over 4. So that's how we find the angle. So we have r and then we have the angle, so we can write it in this polar form. Now when we need to compute the power of this complex number, well, it's power of this expression here. So it is this expression to power 10 and then obviously this expression to power 10. But we already know that this is just the 10 times the angle actually. So we multiply angle by 10 in each piece and that's it. And then we can simplify eventually. Here cosine 5 pi over 2 is 0, and for this guy is 1, so that's why we end up with this number here. So obviously there is no point of trying to compute this product, the number times itself 10 times. That would be extremely long. So we use the polar form, and then we put the polar form to the power 10 through the property r to the power, and then cosine of the angle n times, so the power times the angle that we had. So simple procedure, and that's why this form, polar form, is very useful, as well as Euler notation. So another example, complex number to some very high power. Again, this is a complex number 1 minus I, so this number, we are on x-axis positive and y-axis negative, so we are in the quadrant number 4. So when we pick the angle, we need to be mindful of that. The modulus, as usual, the first a squared plus b squared, here b is minus 1, radical, so we have our modulus, and then for the tan of the angle we have minus 1 over 1, so minus 1, and we pick the angle that is in the fourth quadrant. When we compute here tan inverse, we take minus pi over 4. So now we have our polar form. This is here compacted Euler notation, but this is our polar form. So when I compute z to power 100, is z to power 100 here. So it's radical 2 to power 100, so 2 to power 100 divided by 2, so 2 to power 50. And then we said we multiply by 100 the angle simply. So if we multiply by 100, 100 divided by 4 is 25. So that's why we have 25 here. So from this point on, we figure out what's happening. 25 is 24 plus 1. So if we spin, 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 and then we have 1 pi left. So that's how we get this. So essentially, the use of this polar form, polar notation, is to compute the high powers of complex numbers. It's very easy to apply. Another example, so the complex number could be more or less complicated, doesn't matter. Here, just to realize, we are minus 1, so minus 1 on x and 1 on y, so we are in quadrant number 2. So our angle needs to be in quadrant number 2 when we find the angle. Modulus 1 squared plus minus 1 squared plus 1 squared, so not a big deal. So 1 plus 1, 2, and then we take the radical, so we get our modulus. That's easy. And we remember that angle needs to be in the second quadrant. So tan inverse needs to be minus 1. So we remember we are in second quadrant, so angle is 3 pi over 4. So that's why it's important to sketch a little bit our complex number in a plane to be sure that we pick the correct angle for the correct quadrant. So once we have this written in polar form, it's not complicated to put to any power now, because the r is to the power, here 30, and then this part to power 30 is just 30 times the angle. So that's why it's important to really have the correct angle. So that's what we have here at the end, and then we simplify a little bit to find final expression. So these questions are normally not too complicated, just need to follow the procedure. Another one, so x is negative and y is negative, so x is negative, y is negative, so we are in quadrant number 3. So we need to be mindful when we compute the angle to be in the quadrant number 3. Here, to compute the modulus, so the first part, real part squared, imaginary part squared, and then radical, we add them, we get the modulus, fine. And then we need to compute for the angle, so tan of the angle is b divided by a, so it is radical 3, and we pick the angle in the third quadrant. So here modulus was 1, so 1 to power 15 is still 1, so that's why we don't write it, it's not not a big deal, it's just 1. So the procedure said that the angle needs to be multiplied by the power, so angle multiplied by 15. So 4 times 15 is 60, divided by 3 is 20, that's why we have this. And then we simplify the expression. And that's how we answer these questions. Step by step, important thing is to locate the point on the plane and see in which quadrant we are, because it will be important for the angle. So those are some practice problems, not complicated. So we have 3 ways of writing our complex number. Standard way of writing, we have polar form, polar expression, and then we have this more compact Euler expression. So some practice is needed, but normally this is not too complicated.